Hello everyone, and today let's start with an activity like how many things do we have around us. So probably I have, let's say, a pen, a duster, actually two pens and one duster, so that makes 1, 2, 3. And why don't you also count things around you? And yes, I have this, so I have 1, 2, 3 and 4 and a few things over here. And yes, so how many things can we count actually? Like 1, 2, 3, 4, 5, 6, and yes, around 6. And so what I'll do over here, I'll just note this number so that I don't forget. I'll write that I got my numbers, like I started with 1 and then 2 and 3 and 4 and 5 and 6. Now I'm sure you would have got a similar pattern, that probably we started with 1 and then we started with 2 and 3 and 4 and 5 and 6. But yes, I'm probably hearing that somebody is saying we got 7 and yes, 8 and 9 and 10. But then it can keep going on, right? And it can keep going on till which number? Oh yes, okay. So somebody is saying it can keep going on till 20. And then till, let's say, 30, and obviously yes, 100. But what about further? Can it keep going on? Exactly. So it can keep going on till something called this sign infinity. Yeah, infinity. But now this question I have, that since all of us started with these numbers like 1, 2, 3, 4, 5, 6, all of us started with 1, 2, 3. So did I have to teach you this, or it came naturally to you? Yes, it came naturally, right? So what name can we give together? Well, yes, I do know that they're used for counting. So one name could be counting and the other name could be, yes, exactly. So we can call it natural numbers. We can call it natural numbers. So I'll put a circle over here and I'll circle this. Now, something is missing out of these numbers, and we do have this chart over here, if you see carefully, that what is missing in natural number can be satisfied with lower numbers. So what is missing over here, and what can be the condition? So the condition could be like we have two things over here and they are removed. So when they're removed, they get cancelled and we are getting 0. So, oh, we don't have 0. So what if I add 0 over here and I continue with these numbers like 1 and 2 and 3 and I keep going on till infinity? Yeah. So now I feel, okay, something is kind of complete. Yeah. So now when something is complete, it seems that, okay, it's whole. Yeah. Like something is not there in your life. Like I don't had a bicycle, and when bicycle came into my life became easy. So I'll say, okay, my life became whole. So I'm feeling quite whole in my life since I can ride a bicycle, I can move from places. Yeah. So what name can I give? Yes, I can give it name like whole number. So probably I'll write with this. I got whole numbers. So whole numbers start with 0, then 1 and 2 and 3, and it keeps going on this way. But now there are some numbers missing, and since we are discussing about number system, so which numbers are missing over here? And yes, we can circle this way as well. Now when we circle it in this fashion, what does it indicate? Yes, it indicates that all natural numbers are part of whole numbers, but all whole numbers, are they part of natural numbers? Well, not. Why? Because yes, something is missing. So I do have 1, 2, 3, 4, 5, 6. I do have 1, 2, 3, 4, 5, 6, etc. But yes, this very important number 0 is missing in natural numbers, and that's where we had whole numbers. Now what if I got a question like I want to take 3 things out of 4 things? Is it possible? Well, let's say I went to a shop here and I'm buying something for, let's say I need 4, but I'm just giving 3. That is, I'm giving just 3 rupees but I actually need stuff for 4 rupees. So what happens, since shopkeeper knows me, he might give me all the things, but he might say that, okay, your 1 rupee is remaining. So when I am buying stuff actually and my 1 rupee is remaining, so what I can write that this 1 rupee I can give to the shopkeeper later. Now what does that mean, later? So he or she may write a negative sign in his book and say that, okay, this negative sign acts as a loan. It acts as a loan. So these negative numbers are also needed. Now what I understand, okay, negative numbers are needed, they're not here, so probably I need negative numbers. Okay, so let me rub and make a new number system in which probably I might add some negative numbers. So which is the first I'll start with? Let's say I'll start with 0 and then 1 and 2 and 3 and keep going on till infinity. But which are all these numbers? Are these negative numbers? No. Why they are not negative numbers? Because yes, we know that negative numbers don't hold a tag. Negative numbers are there, but not necessarily you will always find negative numbers. So when some numbers are there like 1 and 2 and 3 and they don't have any sign, so what we can do, we can put a sign over here. So now since we don't have any sign that is on their head, they're not saying that we are negative, yeah, so we assume that they are positive. We assume that they are positive. So what we can do over here is that we can say all these are positive numbers. All these are positive numbers. But what about the left hand side? So yes, on the left hand side we can place the negative numbers like -1 and -2 and -3. Now when we put the negative numbers on the left hand side, we can write that these are negative numbers. These are negative numbers. Now this whole set, that is all this whole group of negative numbers plus 0 and plus positive numbers give us something called, as we mentioned, integers, and I'm sure we studied this in earlier classes. So we write, okay, these numbers are called integers. These numbers are called integers, and I'll circle this whole over here like this. Okay, but now still I feel something is missing. So what exactly is missing? Can we imagine like what's missing? Okay, yes, I remember when I'm eating something, yeah, and my friends come, probably I share some portion with my friends, yeah. So what does that lead to? Okay, that leads to some fraction. So yes, my fraction part is missing probably. My fraction part is missing. So probably what I can do is I can write these numbers again over here, like I can write 1 and 2 and 3 and 4, and I can divide them into fraction. So let's say I'm dividing this by 2, so I get 1 by 2 as a fraction. I can write 2 by 3 as a fraction, or 3 by 7 as a fraction, any number. So this comes into a numerator and a denominator form, but I still feel something is missing. So what is missing? Okay, I've done this part. Oh, 0 is missing, so I'll write like 0, but still something is missing. So what I feel is, oh yes, obviously we got these negative numbers, but now since we're dealing with fractions, and fractions are positive essentially since they have the numerators as whole numbers. So what do? Well, don't think much, just copy them. We'll think later. So 1 by 2, 3 by, let's say 8, or 5 by 9, or 4 by 9, let's say. But I have some confusion that I have 1 by 2 over here as well, and I have 1 by 2 here as well. So which 1 by 2 shall I look into? Shall I look this as positive, or shall I look this as positive? Okay, so I do know that my right hand side was a positive and my left hand side was negative. Oh yes, I get. So I'll put these as negative numbers, like -1 by 2, -3 by 8, -5 by 9, and -4 by 9. So yes, when I get these set of numbers, like I get some negative, you can say negative fractions if you want, I get 0, and I do get fractions. Their whole combination makes something called rational numbers. They're called rational numbers. So yes, we can make this whole circle, and you may also want to look at this beautiful chart over here, and we may say that all natural numbers are part of whole numbers, and all whole numbers are part of integers, and all integers are part of rational numbers. But are all rational numbers part of integers? No. Why not? Okay. Oh yes, because in integers we don't have fractions. Yeah. Are all integers part of whole numbers? No. Why not? Because oh yes, we don't have negative numbers. Are all whole numbers in natural numbers? We discussed. We don't have, because we don't have 0. So what we can say is that all natural numbers and whole numbers and integers and all these numbers will essentially form a bigger set, which is a rational number. So we can see it this way. Now one question I do have over here, that what if the 0 was being divided by 4? Is it possible? So let's see that possibility, and I'm sure you're taking notes. Yeah. So let's try to rub this. Let's try to rub this and see the possibility if 0 can be divided by a number. Yeah. So let's rub and try that possibility. Okay. So now I'll write 0 over here, and what I was discussing, that can it be divided by any number, and since I'm just taking example of a number called 4, let's take example of 4. And how can I divide it? So let's say I'll put 0 inside because it's what I want to divide, and I'll take 4 outside because it will act something called divisor. Divisor is something which divides the number above, and let's try. So the division goes this way, that you need to multiply something to the divisor so that it makes a value either equal to the number inside or lesser than that. So if I say 4 ones are 4, it gives me a high value, so I can subtract 4 from 0 unless until I'm solving for integers, which I'm not in a division. So what shall I do? Okay, I get this, that probably I can make it equal. Now how can I make it equal is probably by trying 4 zeros are 0 and the remainder is 0. That means exact division. That means exact division. So yes, if you have 0 above and you divide by 4, you get the value 0. Now what about if you have 0 above and you get 19? Again 0. If you have 0 above and you get 999, again 0. Very nice. You guys are very smart. Very nice. Now what if I just flip this side and I'll say that okay, let the 0 be there. Yeah, let the 0 be there, and the only thing which I'll do is let the 0 be there, but it will be in denominator, that is below, and I'll just take 4 above. Okay, so I am hearing somebody saying the value would be 0. Okay, why not? Let's try. The value would be 0. But can I just put the value 0 without thinking? Well, never do anything without thinking. Otherwise, you'll burn your meal. You will put somebody into trouble when you just drive without thinking, you know, rash driving and all that. So always think before doing. So I'll think and I'll just not write this answer before thinking. Probably I want to try, yeah. So let's say I'll put this 4 inside because this is what I want to divide, and I'll put 0 outside because this is what I want to use for division. And what I want to see, that what do we get the answer. So let's say the same thing I know, that 0 has to be multiplied for division so that I get something equal to this or less than this. So 0 table goes like this, that 0 ones are 0, or 0 twos are 0, or 3s are 0, any number. So I can just start with my lucky number. My lucky number is 9. So I'll just rub this So I'll say, anyways, you're going to get 0. So let me start with my lucky number. You can start with your lucky number. So that could be 9. So I'll write 0, 9s are 0. And what's your lucky number? Okay, somebody said 7. So 0, 7s are 0. And yes, if you subtract, you get like this. So 0, 9s are 0, I get 4 after subtraction, 0, 7s are 0, I get 4 after subtraction, and 0, 6 are 0. And what will happen? This will keep going on. And this will keep going on. Now, do you really think that this system can give you any kind of answer, any stable answer, let's say? Not? Okay, so I'll say no stable answer or no fixed answer. Okay, so when you are not getting no fixed answer or no stable answer, can you say that you can define the value of 4 by 0? Can it be defined? Okay, if it cannot be defined, so can I say, since there cannot be any definite answer, because if you just started with 7, then it would be 7. If you started with 8, it would be 8. It would be the 4. So there is no definite answer to this. So this means there is no defined, there is no specific definition to it, you can say. There is no specific definition to it. And what is the definition? That for a certain thing you can say specifically what you can do, and there is no specific definition. So when you cannot define it, can I say it cannot be defined? Yes, I can say thank you. Thank you for helping me. So I can say it cannot be defined. And guess what? We just proved that 4 by 0 cannot be defined. You don't need complex logarithms to prove it, right? Or complex calculus. It might come later on in 11th or 12th. So now we have come to very important conclusion that P by Q, that is P being my numerator and Q being my denominator. Yes. So this P by Q, where P and Q are integers, but Q is not equal to 0. So can you let me know why this rational number, which is defined over here, it can be P by Q, but this Q cannot be 0. What happens when this Q is 0? So what happens is, when this Q is 0, it cannot divide the number above. And that's why when we have rational numbers or fractions, let's say, we cannot divide that by 0. So you should remember, if 0 comes in numerator, the answer would be 0, which we did a minute back. But if 0 is in denominator, you cannot use that 0 to divide the number above. It just cannot be defined. And sometimes it is also used in our world, mathematical world, to say that it's undefined. It's undefined. And you know what? I have a little story for you. This little boy, I'm not sure if he was Srinivasan Ramanujan or some genius boy. He was studying in his class and the teacher was telling a story. So teacher told, okay, what if I have 10 bananas with you? So the teacher told, what if I have 10 bananas for you, and those 10 bananas you have to divide equally among 10 children. I repeat, what if I have 10 bananas for you, and those 10 bananas you have to divide equally among 10 students. So when you divide 10 bananas among 10 students, how much each student get? Obviously, everyone said 1 banana each. And what if you have 100 bananas and you're dividing among 100 children? So how much each student get? Again, 1 banana. And what if you have 1,000 bananas and you divide 1,000 bananas among each student? So everyone said 1. Now this little child, he raised his hand and he said, sir, I have a question. So the teacher said, yes, what is the question? So he asked, sir, what if we have 0 bananas and we divide it among 0 children? And guess what? The teacher said, well, I'm not sure, but we'll find it out. And you know what, in that time, the greatest of the mathematicians, they were still discussing, they were still analyzing, they were still debating that what should be the answer when you divide by 0. And I guess, I'm not sure how the Ramanujan figured it out, but we certainly figured it out today, that if you divide by 0, it would be undefined and it can go up to infinity. And since it can go up to infinity, so sometimes some mathematicians used to say that, okay, if you divide by 0, the answer would be infinity. So someone will say the answer will be infinity, someone will say it cannot be defined, someone will say it will be undefined. It's all same. Let's proceed. Now, we have some property over here which we'll discuss in rational number, and one property over here is commutative property. So let me just make some room over here and discuss what is commutative property. Okay, so let's say we have two numbers over here which we are discussing, and these numbers are 2 into 6. Now as you can see, we see over here a few apples which we can replicate over here. So we have 2 into 6, and you can replicate that in a form that you can make two rows like row 1 and row 2. Why? Because you have 2 over here and you can get 6 columns. So you can get column 1, column 2, column 3, column 4, column 5, column 6. And we'll arrange our apples in such a way. So we have 1 apple, 2 apple, 3 apple, 4 apple, 5, 6, 7, 8, 9, 10, 11, and 12. Now the question over here is that this 2 into 6, will it be same if it's reversed? That is, instead of 2 into 6, you would want to write 6 into 2. So if I write 6 into 2, one thing is we can try multiplication, the other is we can just reverse it. So what if I hold it like this and I reverse? Yeah, just hold it like this and reverse. I hold it and reverse. So what happens? My rows will come above and my columns will come like this. It will just reverse. But anyways, we can draw again. So it would be like this way. Let me draw black apples just for a change. So I'll write, okay, 1 row, 2 row, 3 row, and how many times? Like it would be 6 times. Okay, so 1, 2, 3, 4, 5, and 6. And how many? Obviously, you can count 1, 2, and 1, 2, 3, 4, 5, 6, 6 into 2, 12. So the commutative properties essentially states is that when you reverse the values, you will get same number. So whether it's 2 into 6 or 6 into 2, your value will be same, which is nothing but 12. In relation with commutative property, we do have associative property as well. And what does associative property say? Let's take any numbers like 2 and 3 and 5. Now, if we want to add it, let's say using associative property, so probably we can make some groups. Let's say I'm first adding these two, and the third number I can add later. Yeah. So I'm getting the answer like 2 plus 3, 5, and 5 plus 5, 10. Right? Now, according to associative property, if you just change the grouping, that is, now you're doing a different set of grouping, like you leave this 2 over here alone and you take 3 and 5 as a new group. So when you take this as a new group, you would get 3 plus 5 as a new group. So you can put 2 over here and you can add 3 and 5. And here's 3 and 5, we know 5, 6, 7, 8. So this would be 8, and 2 plus 8, we get 10. And both of them seem to be equal. So according to associative property, if A plus B plus C is equal to A plus bracket B plus C, then yes, both of them are equal according to associative property. Now these were from these examples are of natural numbers, or let's say whole numbers, but it holds true for rational number as well. Now how can we prove that? Let's delete this and let's try, and we do have another chart which will help us to analyze this, and this chart is over here, that if I have 3 by 4 and I have 1 by 4, which I can very nicely draw over here. I have 3. So first I divide by 4 into 4 pieces, because in total I have 4. And if I have 1 part, 2 part and 3 parts, so I have this 3 by 4, and it's getting added over here to 1 over 4, which I write like this, and it's getting added. It's getting added to 1 out of 4. So according to this commutative property which we just discussed before, associative, this should be equal to the reverse. And what could be the reverse? That I write, instead of 3 by 4, I first write 1 out of 4. So I write 1 out of 4 over here like this, and then I add again, and I make again a circle. And by the way, all of them must be of equal size, but we are just making approximate over here. So this should be 3 out of 4 over here. So I make like 1 part, 2 part and 3 part. And what commutative property in rational number as well say, that 3 by 4 plus 1 by 4 must be equal to 1 by 4 plus 3 out of 4. Why? Because if you join these two, it will give me a whole, and if you join these two, it will give me a whole. And yes, you can calculate as well, like this will be 4 by 4, which will be nothing but 1 after cancellation, and it will be again 4 by 4, which is nothing but 1 after calculation. So that's some properties regarding rational numbers. And now I do want to discuss a subtopic of rational number, which is additive inverse. Now what does additive inverse indicate is, let me just put it over here. So additive inverse indicates that one number is negative of the other. And let me make some space and try to explain this, that how is this possible. So I'll make some room over here. I'll delete this, I'll rub this, and let's try to understand what does additive inverse imply. So let's take an example which is given, like I have this number 2. Now this number is negative of minus 2. What does this statement actually mean? So this means that currently it's not negative, it's actually positive. So we can say plus 2, let's say. So I can say plus 2 is negative of, means I'll put a negative sign like this, and of means that I'll multiply like this, of minus 2. So I'll put minus 2 over here. Now if we have discussed integers below, if we have discussed integers in an earlier video, we know that when a negative gets multiplied with a negative and both are same signs getting multiplied, then their value will be plus. So what I'll do is that I'll multiply, and as per my knowledge of integers, I do know that negative into negative will make it plus, and this will be plus 2, and yes, I started with plus 2, so this means plus 2 is plus 2. So as we discussed that 2 is negative of minus 2, what it indicates that plus 2, when you apply that it's negative or minus 2. So minus into minus multiplies, as we discussed, it's a property of integers, and they multiply, same signs multiply to give me positive. Now if you take the reverse, that negative 2 is negative of 2. So how can you say that? You can write it this way probably, that negative 2 is equal to negative of this number, which is plus 2. So what does it mean? That this sign over here, actually what it means is that this sign over here, it's actually getting multiplied to a number, and that number itself is not negative. Are you getting? Sometimes in our life we do a lot of positive things, but one negative thing puts a label on us that, oh, this guy, this girl, this child, this man, that negative. But actually we are not negative. Situations might lead us to fight, to shout. So actually this number was positive. If you see, this number was actually positive, the situation was negative, and same you can see over here that this sign is negative but the number is positive. But the situations are such that the negative situation makes a positive person negative, so it becomes negative 2. You say, oh, he's a negative guy. Yes, he or she seems to be a negative guy as per the situation, but there is always a possibility to become positive later. Now we are done with it with additive inverse. We also have reciprocal, which is also called multiplicative inverse. Now let's take example of that, and let me make a room over here. And what we can do is that, let's say I have a number, let's say I have a number 2 by 3. I have a number 2 by 3. Now I want to find something called reciprocal. And what reciprocal means is that you'll try to take 3, which is denominator, into numerator. So if it is denominator, it will become my new numerator, and if this is numerator, this will become my denominator, and that way I get a new number, which is 3 by 2. And how can we confirm that this 2 by 3 can make the reciprocal as 3 by 2, or the 3 by 2 is reciprocal of 2 by 3? How can we confirm that? So there is a way. When you multiply both of them, that is, if this is your original number 2 by 3, then you write 2 by 3, and when you multiply with its reciprocal inverse, or it's also called multiplicative inverse. Multiplicative inverse. So if you multiply with its multiplicative inverse or its reciprocal, the final answer, 3 ones are 3, 3 ones are 3, 2 ones are 2, 2 ones are 2. So 1 into 1 is in numerator, 1 into 1 is in denominator. What do you get? You get 1 by 1, ultimately you get 1. Now, sometimes things are not favorable, they are exactly opposite, and they are, let's say, I'm a very bright guy, and my school teacher gave me a partner who is not that bright. Or I'm very bright, but my brother, my younger brother, is not that bright. And I feel, oh my God, what a pathetic, what a difficult team, or what a pathetic situation it is that, we make no match. But remember, when you multiply, what are you getting? You're getting a whole, because 1 is a whole. So probably we can learn from multiplicative inverse and reciprocal that when one person makes team, multiplies with a person which is totally reciprocal, totally opposite, still you can make a good team as you're making one whole. And let's go back to our next topic, rational numbers, where probably we will stick it over here and try to understand that what are rational numbers, or how can we represent that into a number line. So let's make some space, and essentially we'll be trying to draw a number line and see if we can get some analysis out of the number line. So I'll emphasize and request that do get your pen and paper and work together so that we can analyze on a number line, right? And let me just rub in between. So I'll make some space over here and we'll be drawing a number line. Let's say I'm going to draw a number line and choose the numbers. Let's say I'll make a number line like this. Let's say my first number line is like this, and the arrow on the left hand side and the arrow on the right hand side indicates that the lines are keep extending, they keep moving on the left hand side, and the right hand side it's not finishing. So let me start with the neutral number, which is 0, my neutral number, and probably on the right hand side I want to put a few numbers more, which are like 1, and we know by now that they're positive numbers. So I have +1 and +2 and +3, and it will keep going on till infinity. And similarly on the left hand side I'll take the numbers as -1 and -2 and -3, and obviously they will keep going till -infinity. So this is one of the number lines. Now what I want to analyze in this number line is that can I find some rational numbers, or it's just a story? So let's try to do that. So what probably I want to do, that I want to concentrate on this portion over here. Let me take another color and just emphasize that I want to emphasize between 0 and 1. So let me just put a dot over here and try to see if I can make some space from 0 to 1. From 0 to 1. Now, probably between 0 and 1 over here, if this is 1 on the right and this is 0 on the left, I can divide probably into 3 equal divisions. So I'll see 1 and 2 and 3. And you can also try this way with your hand, approximately 1, 2 and 3. So I'll divide like 1 and 2 and 3. Now if you are approximately making into 3 equal divisions, this is my 1 and this is my 0. So what do you think this part would be? What do you think this part would be? Exactly, this would be 1 out of 3. So I'll say 0 and this would be 1 out of 3. Now if this is 1 out of 3, so what could this be? This could be 2 out of 3. And now what happens to this? Okay, let's start again. If this is 0, and if this portion over here is 1 out of 3, this portion is 2 out of 3, then what could be this? This is 1, and I'm kind of confused. Let me also think, oh my god, I'm stuck, what should I do? Okay, I got it. So what I'll do is, if this is 1 out of 3, if this is 2 out of 3, so yes, this should be 3 out of 3, and we know 3 by 3 is nothing but 1. So now we understand that yes, between even natural numbers like 0 and 1, we will have some rational numbers, right? Between 0 and 1, which seem to be very small over here, we do have, when you magnify them, you understand that yes, there are some rational numbers. And now probably I want to try between a few points. Let's say I'll delete this again and I'll see if I can find some more rational numbers. So let's delete this and try to analyze that. If my first point is 0.3, now what does 0.3 means is in fraction, we have already studied, it's 3 by 10. And we'll try to take it again and extend it till here, and probably I want to take the next point as 0.7, and it's nothing but 7 by 10. So essentially we have 2 points, one 3 by 10 and one 7 by 10. And the question is that how many rational numbers can come between them? By the way, first we want to be assured that will we get any rational numbers? Yes, thank you for that. We'll get rational numbers, but how many rational numbers can we get? So one way could be that probably I want to add both of them here. I want to add both of them and divide by 2. So probably I'll say, okay, this is 3 by 10. So 3 by 10 plus 7 by 10. So I'll take, okay, this is like 0.3 and this is like 0.7, and over here I can find 0.5. So yes, by this we can understand that if it's 0.3, this would be 0.4, 0.5, 0.6. Okay, so I do find some relation that after 0.3 gets 0.4, you get 0.5, you get 0.6, and you get 0.7. But now, can there be more rational numbers, let's say, between these regions? Or can there be more rational numbers between 0.5 and 0.6? Or can there be more rational numbers between these? And yes, I think yes, there can be many rational numbers. Now let's try to, again, like scientists and researchers, let's try to emphasize and focus on small spot, and probably I'll give you some example, and probably this is our last example, and we'll try to focus that what if I'll try to analyze that 3 by 10 and 3 by 100, which is bigger out of them? So probably we'll want to put it into decimals, and we know, okay, this is 0.3 and this is 0.03. So obviously 0.3 is bigger. And probably if I want to extend it this way, that we also have 3 by 1000. So what we can say, okay, we get 0.003. So obviously 0.3 is bigger than this. And what if we extend it to 3 by 10,000? So we can say, okay, it's 3 over here, and I will know how to share it. We learned in class, like I put 1, I count number zeros, 1, 2, 3, 4, and 1, and 1, 2, 3, and point. So yes, so probably we can say that 3 by 10,000 will come in between somewhere over here. Yeah, and it can extend to, let's say, 6 by 10,000. So if I have 3 by 10,000 over here and we have 6 by 10,000 over here, so how many numbers could be here? And roughly, I think if you calculate carefully, you'll come to know that there will be like 3,999. But what if you take new examples, and instead of 3 by 10,000 you keep on increasing the zeros, like 1, 2, 3, 4, 5. So there is no limit. It says sky is the limit, but even the sky is not limit. So probably what we can say over here, that as and well the decimal places keep on increasing, our rational number between these tiny and small parts will keep increasing as the decimal number keeps increasing. So we can say that any two numbers, whether decimal or whole number, whatever, they will have rational numbers which are uncountable, And welcome to the world of numbers and rational numbers, and I'm sure in coming topics and classes we'll study more about it. Thank you.